All right, so on station 3, we're going to talk about graphing systems of linear inequalities. So a linear inequality is it's written like a linear function, but we have solutions that are on one side of the boundary line. So the first thing we do here is we graph our boundary lines. And to graph the boundary line, I just kind of pretend it's an equal sign. So I graph my boundary lines. And you don't have to write this down every time, but I'm going to graph the two lines, y equals 2x minus 1 and y equals x minus 2. So 2x minus 1 has a y-intercept of -1 and a slope of 2. So that's 2 over 1, right? So rise 2, run 1, 1. Here's my 2 points. So there's my first boundary line. Let me switch to another color here. Okay, and then my second boundary line is x minus 2. So has a y-intercept of -2 and a slope of 1. So that's 1x. So it has a slope of 1, so rise 1, run. So there's my other boundary line. All right, so those are my boundary lines. Now I have to figure out my shading. So this says that and I'm going to come back to that second line because that needs to be dotted. So when y is by itself, if we have slope-intercept form, I can't spell, itself, so y is isolated, then we can just follow the rule greater than, shade above, and less than, shade below. So both of these are solved for y already, so I can just follow that rule. So the first one says y is less than or equal to 2x minus 1. So I just shade the part below that, which would be here. The second line says y is greater than, but not equal to x minus 2. So I actually need to redraw this line. It's the same line, but it needs to be a dotted line because it's greater than, but not equal to. So use a dotted line. And it's just to communicate that the points on the line are not solutions. So for the same reason, we use an open circle when we solve one variable inequalities, because we're not including on the line. And here, use a solid line. Anyway, it says y is greater than, so I just shade the part that's above that. So all the way over here. So that's the entire second inequality. And then my solution region is where the solutions to both inequalities are true. So our solutions and that's going to be where both parts are highlighted. So I'll go over this again. So here is the region that I have green and purple shading, so that's my solution region. So every point in there satisfies both inequalities. So for example, 5, 5, 8, 10, etc., right? So any of those points that are in that blue region where both inequalities overlap. All right, so the second one, same idea. Now the lines are not in slope-intercept form. So just like with graphing, I have two options. I can solve for y. So y is not isolated. So we can solve for y, or graph using intercepts. And I'm going to do both. So for the first one, I will solve for y. The second one, I'll do the intercepts method. So if I have, now in the boundary line, actually, because we're manipulating an inequality, so if I want to get y by itself, I subtract 2x, subtract 2x. So now I have negative y is less than negative 2x plus 1. I don't want to solve for negative y, I want to solve for positive y. So I need to multiply both sides by negative 1, or divide both sides by negative 1, it's the same thing. And because I divided by a negative, my inequality sign is reversed. Now that's 2x minus 1 when you distribute to both. And this is one of the reasons I personally prefer using intercepts when I graph inequalities, because I don't have to think about switching the inequality sign. But you do whatever you want to do, right? So just remember that we flipped the inequality because we multiplied by a negative, or divided. Okay, so y is greater than 2x minus 1. I didn't mean that for that to be the same as the previous one, but whatever. And it's a dotted line because it's not equal to. So use a dotted line and shade above because it's a greater than sign. So 2x minus 1 looks like that. And my shading is up here. All right. And the second one, you could also solve it for y and graph it that way, but I just want to show how you can graph inequalities using the intercepts method. It requires one extra step. So first, solid line, right? My x-intercept is going to be when y is 0. So 2x equals 6 and x is 3. So my x-intercept is here. And my y-intercept is when x is 0. So then 3y equals 6 and y equals 2. Now I use a solid line because it's greater than or equal to. But now, since y is not by itself, I can't just say it's a greater than sign, so shade above. What I actually do is I test a point. So I'm going to test the point 0, 0. So if I plug in 0 for x and 0 for y, I get the statement that 0 times 2 plus 3 times 0 is greater than 6, which says 0 is greater than 6. Now that statement is false. So that tells me that 0, 0 is not in the shaded region. And the line divides the thing into two regions. So if this point is not shaded, then neither is this point, or this point, or this point, or this point, or any of the points on this side of the line, right? So that means that all the points on the opposite side of the line are shaded. So every point in the region that is not shared by 0, 0 is shaded. And then, once again, I see that my region where both inequalities are true is up here. All right, so again, you don't have to graph by intercepts. You can solve everything for y, or you could graph everything by intercepts and do the testing of a point. Whatever works for you.